So hello everybody, thank you for joining this session. I share my screen. Okay, the topic for this next session is off-the-shelf IP cores for cameras and embedded vision. And Eric already mentioned some overlapping of our products and technologies. I want to go a bit deeper into this FPGA IP core stuff. First, a few words about sensor to image. We are founded in 1989 as specialists for machine vision hardware. We started with frame grabbers and ESP-based processing boards. FPGAs have been used as soon as they are widely available. So it was a logical path for us to invest more here and to offer standard products for FPGAs. So we started in 2008 with FPGA IP cores for machine vision applications, especially for transport layer standards. And in 2008 we started with GigE Vision as an IP core. Now we have a bunch of IP cores available, and we are one of the providers which offer all of these major protocols like GigE Vision, USB Vision, CoaXPress, and a few sensor interfaces. And we are part of these standardization committees for these standards and claim to be up to date here with all these technologies and involvement what are going on. Since 2017, we are part of the Euresys group, so we have a wider force and reach of our products and yeah, a new country. My name, as mentioned, is Matthias Schaffland. I'm the product specialist for the IP cores. So in case of any questions now or later, just contact me. I want to talk first about a typical architecture of FPGA-based vision systems. So the main components, of course, there are always some differences, but the main components and to map them with a typical design using IP cores. Then we have a look at typical IP cores, which are available for FPGAs. Three main topics we have here. First is this transport layer IP cores. So that means how to transfer images out of an FPGA, out of a component to another system. Then IP cores for sensor interfacing. We have heard about MIPI. This is of course one, but not the only one. So here we have different options. And also some words about what is available or possible around image processing. As we are offering some of these IP cores, I want to demonstrate the typical design flow when using a GigE Vision IP core as example. To give you an idea what is provided with an IP core, what is still to do. And finally, some ideas about time to market considerations, what effort has to be done if you want to do it from scratch, or what benefit you get if you use components, IP components. Okay. First, a typical architecture of a camera system. Looks like that here on a very high level. We have, of course, an image sensor from different type, MIPI or something else. Then we have a processing part. This could be an FPGA, that could be an SoC, this could be a CPU system. So this is independent so far. Within this processing part, we have a sensor interface, so we need an interface to the sensor to read out and control the sensor. Then we use an image processing part to have pixel pipelining, maybe process the image, a real processing of the image to get out the data. And finally, we have an output interface with a transport layer that could be CoaXPress, GigE Vision, USB3 Vision, but of course, MIPI or other protocols are available as well. On top of that, we have a kind of camera control, which is responsible to control the sensor and all these sub-modules like sensor interface, image processing, output control. In a way, all camera systems look like that. An embedded processing system looks a bit different. Here we have an external camera with an interface like CoaXPress, GigE Vision, USB, or MIPI, or something like else. We need inside our processing here, the blue processing block, a camera interface, not only a sensor interface, but a camera interface to implement these protocols, what is used by the camera. And this camera interface also does the protocol decoding and exposes the image data in an easy way for further processing. So we use, or then we have an image processing block, what was discussed in the previous section. And at the end, we could have a machine interface to control some IOs, some PLCs, go on a field bus, or maybe we just retransmit the data using a MIPI interface, or again, something like GigE Vision for further processing on a different computer. On top, again, we have a remote camera control unit to connect to the external camera, something like discovery or configuring the camera, get it streaming, setting exposure time, all this stuff. This is done in that block here. And of course, it also should or has to control the underlying blocks for the processing. What FPGA cores are available? Mainly from us, transport layer cores. Here we offer GigE Vision for cameras and receiver. GigE Vision, you know, this is a protocol, meanwhile, 12, 13 years in the market, starting with 1 GigE Vision. Meanwhile, we are at 10 gigabit vision and 10 gigabit speed. And the evolvement is going on for 25 and even more gigabit. So this is available for FPGAs, and not only for cameras, but also for receivers. Similar for USB Vision. USB3 Vision is a standardized protocol from our machine vision industry using the original USB3 protocol with some extensions, and currently is in involvement for USB4 as well. CoaXPress from the very beginning is more targeted as high-speed interface, and currently is one of the fastest one with 10 or even more gigabit per lane, per connection. And it could be used for designing compact but very fast cameras and also receivers. This is not only for copper medium, it's already available for fiber connection as well. So we do not have the restrictions about cable length and so on. All these three IP cores are available at Sensor to Image. At third parties, you can find CameraLink HS, which is a standardized protocol, but not so widely used as the three first protocols. On sensor side, we have heard about MIPI. This is a growing interface for sensors. So here, this is available for connecting to FPGAs. MIPI is a bit special from the signaling and so on. So FPGAs have its problems. The newer FPGAs, meanwhile, are capable to directly connect to MIPI sensors. In both cases, MIPI receiver IP core is available at sensor to image. For other sensors, especially the Sony IMX sensor series, they come with different interfaces. An older one is the sub-LVDS interface. Here we offer an IP core, so you can easily integrate that. For other ones like SLVS EC, there are IP cores available from third parties. Image processing is typically, from the point of view of our IP cores, the main differentiation of the cameras. So this is from our customers the point where they invest, or where they have to invest the most of the time, and make the key point where my camera is better than the other one. Nevertheless, there are IP cores and tools available to make this development easier. So FPGA vendors and third parties offer so-called video suites or something similar, which are IP cores for image typically pre-processing. That means tasks like scalar, to resize the image, color transformation, debayering, but also some filters and transformations. These are part of these off-the-shelf video suites. These are only very basic processors and IP cores, so this will not help for all and everything. Some FPGA vendors, meanwhile, offer tools for high-level synthesis. That means you can write your FPGA code in C or C++ language. And with these tools, you are able to directly compile it to VHDL, to RTL. And that makes it much easier to write own image processing functions. So you can take your image processing function that you have done and proven maybe on MATLAB or other higher level tools, and convert them to VHDL and program them at the end into an FPGA. In addition, these HLS tools often include image processing libraries, so not every filter, not every transformation has to be done by hand and from scratch. You can use existing tools and libraries for typical image processing functions. The output of an function done with such high-level synthesis tools is typically again an IP core and can be used the same way as other IP cores and integrated in the typical design flow. How a typical reference design looks like if you go with an S2I IP core. Here I have a block diagram of a reference design, and on the right side on the top, just as reminder, this was the typical architecture of a camera system. So sensor, output, camera control, sensor interface, image processing. And comparing that with a reference design, it looks very similar. So as input, we might have a sensor, but typically it's more a test pattern generator, what is provided as VHDL, and where you can do your own testing and implementing of typical input. After that, we might have a frame buffer IP. This frame buffer IP is responsible to buffer data into external memory and maybe recall some data in case it's needed. It's a bit dependent on the protocol if it's needed or not. And finally, we have a transport layer IP for GigE Vision, USB3 Vision, CoaXPress, or let's see what is coming in the next years. And this transport layer IP is coding the image data according to these machine vision standards. On top of that, we have a CPU system, and CPU system means we have a processor like a microBlaze, NIOS, ARM system, but also we have peripheral controllers like I2C controller, SPI controller, but also memory controller, DDR memory controller to interface to external memory. So if we use a frame buffer here, this is not done, the access to the external memory is not done directly from the frame buffer. We use standard IP cores from the FPGA manufacturer. On the CPU system, we run a device application, device typical application, and this is typical for the lower time critical tasks. Like if you want to set the exposure time of the sensor, this ends up in the CPU system, and the CPU system may program the I2C to configure the sensor, for example. Nevertheless, all these commands come in the protocol encoding, so we have a lower level library included here, and this does all these decoding of the commands. So it's not necessary for you as implementer to know all bits and bytes how GigE Vision control protocol packet has to be coded. This is then, or decoded. This is then done in the low level library. Of course, it's possible to modify this reference design. You see a part of these blocks here are provided as source code, so you are able to modify this application, for example, to integrate new registers, new functionality to your sensor, and of course, in the FPGA part, you can add new blocks and new image processing parts. So typically, the part between sensor and frame buffer or transport layer, depending on the protocol, this is where you put your image processing, image enhancement, whatever functionality, what you need, and what you want to implement in FPGA in this chain. An embedded processor system with S2I IP looks not so different. Going back to the general overview, we have an external camera, then the camera interface, and image processing and output. In a reference design, it's even simpler. We have our external camera, which is connected by CoaXPress or GigE Vision or something like that. Then we have our transport layer IP, and the main part here is to decode the stream coming from the camera. And typically this is exposed as, for example, an axis stream, so you can interface to this stream and do your image processing. As this is not a full system, we typically add a kind of video controller for display, so that you see, okay, my camera is streaming, I see a real image, and this again shows how to use the data coming out of the transport layer IP. On top of that, again, we have this CPU system, and compared to the camera system, this system is responsible to control the camera, the external camera, so something like discovery or speed detection or setting exposure time and stuff like that. This is all done on that CPU system, and typically in C or higher level language, so it's not needed to code somehow in VHDL how to communicate or how to set the exposure time of a camera. So this is much easier here. Again, to code these commands, please set the exposure time of the camera in the correct packet format and so on. This is done using a lower level software library, and so abstracts the use of the IP core. How the typical design flow works with sensor to image IP core, we have different phases. The initial phase, this is guided by us, and here we have to find a common development platform with an FPGA as close as possible to your final hardware architecture. Typically here we use FPGA vendor boards, or if there's no preference and or not possible, we have our own one, the MVDK, the Machine Vision Development Kit. Here we have all major machine vision interfaces available on a single development board. So that means we can provide designs for GigE Vision, CoaXPress, and USB3 on the same platform. We also are able to connect with this FMC extension interface, interface cards with Sony IMX Pregius sensors or MIPI CSI sensors to give you the possibility to really fully test a camera or receiver platform. We support speeds up to 10 gigabit for GigE Vision and CoaXPress up to 12 gigabit per connection. And we support several modules here on this MVDK. You see we have a module here, and here we use a cluster FPGA modules, so we have a bit of choice what FPGA we typically use. It's very important for us that we deliver a full working reference design for the development platform. So our IP comes always as a fully working reference design, not only a simulation module or somehow partially implemented design. This is really a fully working system, so you can program your board, connect it to your PC and see streaming, even if it's only test pattern, but you see the images, and then really can jump start into the design and modify it for your needs. We also provide necessary interface cards like CoaXPress FMC cards or 10G NBSD cards, or as mentioned, sensor interface cards for the development process. And finally, we do an initial training on the reference design. So we have a meeting, similar like here, where we explain in detail the reference design and all the steps going through what has to modify for the final application. When the implementation phase starts, and which is the part the implementer has to do, but you are not alone, we still support you in doing that. So our first step would be to port the reference design to the final hardware with the help of sensor to image. Then dependent on the application, for a camera application, you have to integrate sensor control and readout logic. If it's not an additional IP, you have licensed somewhere as well. And of course, you would like to integrate the product-specific image processing functions like pixel operations, laser line extractions, or even deep learning, or whatever what is needed. This is then all these tasks, which are typically the remaining tasks beside the IP cores, at least from sensor to image. In case of processing board, it's very similar. In a first step, okay, porting the reference design to the final hardware ensures that the design is working, that the hardware is working. Then we have to adapt the reference design for the final camera or cameras. So, and the specific features of the cameras. Dependent on the processing board, this might be a bit more work or less work, depending on if, for example, Linux or something like that could be used to use libraries to work with the XML file. If it's a deep embedded board, then typically no Linux or no further pre-processing of this XML file is used, and then it could be implemented a bit in a more hard-coded way. And the main part, of course, is the integration of the application-specific image processing functions. already had that. Just a few examples what we did in the past using our IPcores, some middle applications, camera link to GigE Vision converter, hardware design, certification, and full production, and of course using the GigE Vision IP, an IMX camera with good old analog PAL output, but also digital 66 output. Here we did the hardware design and the full production, and the customer added his specific image processing stuff. And finally, no, not finally, automotive industry. Here we have a camera platform with MIPI sensor interface. So this is also a sync system, for example. Here we do design and full production and help them to do their image gathering for automotive driving. Machine vision, industrial metrology, scanner system, design and full production, and various processing and interface board designs. And finally, we are also present in space with the GigE Vision IP, for example, for a satellite system, but also for a receiver system where we supported a launch control recording system. A few things about time to market. If you want to do a camera system and using these standard interface protocols, you have to think about at least 6 months of work to implement something like GigE Vision or CoaXPress or so. And that means ongoing work and ongoing maintenance work if you want to be up to date. So this is not a one-time job, and this has to be taken into account. If you take an IP and just port the reference design to your production hardware, this is more in the range of 1 to 2 weeks. Similar with sensor integration. If you do it on your own, okay, depending on the sensor interface, it could be several months. Using IP, it's more again in the range of 1 to 2 weeks. So this is a big part of development time and especially ongoing maintenance work. There are arguments to do it on yourself, but there are a lot of arguments to do it or to buy these components. This is a strategic decision. The integration of the pixel pipeline or image processing, yeah, okay, this is highly dependent on the requirements, so I cannot give a typical time. But as mentioned earlier, this is typically the main differentiation criteria to other products. So if you know, okay, I have this special key feature and no other one has that, this is of course a selling argument. So typically time to market without IP, you have to calculate with at least 1 year with 1 or 2 persons full-time working on that and ongoing work afterwards. With IP, it's more in the range of 1 to 3 months. Of course, it's always dependent on your schedule and manpower and knowledge and so on, but you have the potential to drastically reduce the implementation time. Okay, that's all from my side.